All right, we're back. We're on page 11 of Notes 21, the last page, and we're kind of continuing the previous problem, but only really in the sense that we're still using the same table. So table gives values of twice differentiable function, so that's usually important because differentiability implies continuity. Twice differentiable means the function and the derivative of the function are differentiable, which means they're both continuous. Gives you a lot of information. And we're on the interval from 0 to 14. So the problems we're about to do are, I think, kind of the weirdest of the volume type problems that you can do. So let's see if we can make sense of them and then kind of go from there. So the region bounded by f of x, the x-axis, and the vertical lines 5 and 14. So 5 and 14 is not the full deal. It's just from here to here. So when you read your table, you got to make sure you're reading the right part. To rotate about the x-axis, approximate the volume of the solid formed using a right Riemann sum with 3 subintervals as indicated by the table. All right, so what I'm gonna do is I'm actually gonna copy the table so that I can kind of use it as we go, but I'm gonna struggle to do that. And you can't really see the struggle, so it just looks like I'm fumbling around. All right, here we go. So we're only going from 5 to 14, which means I only really care about this. Which I think is like one of the key parts. Let's just write a definite integral that will give us that volume. So it should be pi, the integral from 5 to 14 of f of x squared dx, right? So now maybe it would be helpful if we kind of created a little scatter plot. It doesn't need to be great, just needs to kind of work. So 5, 8, 3, and 5. All right, so whatever, let's just put a function, something like that. All right, and so that's what we're rotating. So we have our radius, and the radius is always just going to be f of x. So how do we do this? So we have, I will tell you what I think the easiest way to do this is. We're doing pi, the integral from 5 to 14, the radius squared dx. I think the easiest thing to do, we want to approximate this with a what Riemann sum? A right Riemann sum. All right, so I'm going to say this is approximately, or actually, I'm going to say this is exactly equal to pi, the integral from 5 to 14 of g of x dx, where we let g of x equal f of x squared. So why would I do this? I would do this because now I can add a row to my table, which I'm going to call g of x, which is f of x squared. And I'll fill it in for the entire thing. So this would be 4, because I'm taking the value of f of x and squaring it. So 16, 25, 64, 9, and 25. You take the value of f of x and you square it because g of x equals f of x squared. Now all I'm doing is a right Riemann sum to approximate the definite integral of g of x. And it takes this concept, you're not rotating rectangles, it takes the concept and it reduces it down to something that we definitely know how to do. So here I'm going to say this is approximately. All right, so 5 to 7 is 2. And then right Riemann sum? Yeah, so we go from 5 to 7 is 2, and we use 64. We go from, I forgot the pi, so I'm already wrong. 7 to 11 is 4, and then we use 9, so 4 times 9. Let's fix this obvious incorrectness that we are currently experiencing. We got to put in pi, and then that, and then also I'm going to run out of room. Let's move that. Okay, so we did 5 to 7 was 2, and then we pick up 64. And then 7 to 11 is 4 and 9. And then we'll go from 11 to 14 is 3, and use 25. 3 plus 25. 3 times 25 plus 3 times 25 is definitely what my brain meant to say. Okay, and we could leave that, or we can risk it, which I like to do. 75. So let's see. If I add these, I get 203, 233, 239. I think we get 239 pi. But this was risky. I could have left it unsimplified, and that would have been a better choice, but I didn't. Okay, so that's how I like to do this. I like to add the extra function because Riemann sum, like a Riemann sum is fine. A Riemann sum for f of x squared is a little more confusing, but if you define a new function that just is f of x squared, now it's like your normal standard Riemann sum. So I recommend that you do that. All right, how about we go from 2 to 4 about the x-axis again. We're gonna use a trapezoidal sum though with 4 subintervals. So, all right, let's see, do I still have this available? I do. All right, so this time we're going from 2 to 14. So still not doing the whole thing. 2 to 14, and we're going around again. We're gonna use trapezoids. So I'm gonna add again. I'm not gonna name it g of x this time. I'm just gonna do f of x squared, and then that's 4, 16, 25, 64, 9, and 25. All right, because what I want to do is I want to do pi the integral from 2 to 14, right? 2 to 14, yep, of f of x squared dx. That's going to be approximately, let's not forget pi. All right, now trapezoids. So there's a 1/2. And then, so from here to here is 3. And then we add these 3 and 41. 3 times 41 plus from here to here is 2. And we add these. So we get 89. 2 times 89. Plus. So you want to do like a lot of sums. And the more sums you do, the better you get at them. So 4. And then we add these. 4 times 73. I'm going to not add these up. I'm going to use a calculator. And then this is 3, and add these is 34. All right, I won't even make you watch. I'm just going to go for it, which means that I might do it wrong and then just confidently put down the wrong answer. But let's see. It's going to be pi over 2, and then 3 times 41 plus 2 times 89 plus 4 times 73 plus 3 times 34. So this one, I find people find this one more confusing because people are like, oh, we're rotating trapezoids. You're not rotating trapezoids. You're just using a trapezoidal sum to approximate a definite integral. So you're not rotating a trapezoid at any point in time. You have trapezoids, right, that you're using to approximate the area under. So this is the thing. You have trapezoids, and you're using trapezoids to approximate the area under this graph, f of x squared, not under the graph of f of x. So if we were to make a scatter plot for that, this is like the legit way that this works. 2, 5, 7, 11, 14. Because I run into people who I kind of don't understand Riemann sums, I guess. You can have a Riemann sum for anything. Like you're always making like a rectangle or that. So 2, 5, 7, 11, 14, 4, 16, 25, 64, 9. Oh, because I wasn't supposed to start 4. That's why. Ah, boy. Here we go. There. Perfect. 64, 9 again, or 9, and then 25 again. Okay, so this is our function f of x squared, and we're doing a trapezoidal sum for this. So this is where our trapezoids come from. You're not really rotating anything there. You're rotating to get the volume, right? But you're not rotating trapezoids. You're rotating the curve, and then you're going to approximate it with trapezoids. So I think that's like the safest way to think about it. I don't know, your mileage may vary a little bit. All right, the region bounded by f of x, the x-axis, 2 to 11. Okay, so 2 to 11, let's do this again. So we're only going from 2 to 11 this time. So it's not a lot, that's good. Is rotated about the horizontal line y equals 8. Okay, so y equals 8, and then we're gonna use the left Riemann sum. So here's what we're kind of looking at, potentially. You got 2, 5, 7, 11. I'm gonna do a scatter plot for f of x. So here's gonna be y equals 8. 4, 5, 8, and then 3. So whatever, you just have your kind of curve. So the region is here. If you can sketch it, you can do it. I firmly believe that. And we're going around y equals 8. So that's y equals 8. All right, so we're going to get a big radius and a small radius. Your big radius, conveniently, is actually always just top take away bottom, so 8 minus 0. So big R is 8 minus 0. That's fine. Your little radius is going to be here, and that's going to be 8 minus f of x. Okay, so what are we going to do? First, we're going to write a definite integral, because that's, you know, if you don't write a definite integral, you can't do it. So it's going to be pi from 2 to 11, right? 2 to 11, yep. Big radius squared minus little radius squared dx. There. Okay, so what do I need to do? I need to create, well, first let's do this. Pi 2 to 11 of 64 minus pi 2 to 11. Quantity 8 minus f of x squared dx. How could you make your life easier? You can make your life a lot easier by saying, let g of x be the quantity 8 minus f of x squared. So if I do that, then I can add a row here. So I'm going to add 8 minus f of x. And then I'm going to add, first let me move this down a little. Then I'm going to add 8 minus f of x squared. These are championship level problems. 8 minus f of x is 4, 3, 0. And 8 minus 3 is 5. Okay, so what I was doing was 8 minus 4, 8 minus 5, 8 minus 8, 8 minus 3. Square them. 16, 9, 0, 25. So now we have this other function that I'm calling g of x. And I can make a scatter plot for that. So g of x is 2, 5, 7, and 11. It's at 16, 9, 0, and 25. So it's going to be at 16, 9, 0, 25. You know, we don't really know what it looks like. We just know those points. Now we're doing a Riemann sum. What kind of sum? We're going to do a left Riemann sum for this. So we're going to do this, nothing. All right. So let's see if we can do it. So this will be pi times 64 times 9 minus pi. This is an approximation. All right, so from 2 to 5 is 3, and the height is 16. From 5 to 7 is 2, and the height is 9. From 7 to 11 is 4, but the height is 0 because we're doing a left Riemann sum. So we get that. I'm going to use a calculator to just knock out those numbers. And then I think, unless I have some, like, you know, big time fundamental misunderstanding, this should be it. And I really hope that I don't have that, but, you know, cannot rule it out. 3 times 16 plus 2 times 9 plus 4 times 0. I'm typing it. You can hear it. 510 pi. So this is 510 pi. So that is approximately the volume that you would get if you rotated the region. So this is just approximating volumes from a table. It's a little bit weirder than approximating areas. But it all comes back to approximating areas, which I don't know if everyone really picks up on that, right? We're creating a new function and just doing our Riemann sum on that new function. Not really rotating rectangles. We're not really rotating trapezoids. We're using a rectangle sum or a trapezoidal sum to approximate some new function that has these weird values. And I mean, there's nothing really weird about those values, but all right, so that's it. That's it for these notes. I will be back in the next video to work on the next thing. So I will see you there.